So first question to all of you is the quiz results. I think we got 84, 83% passing, and a little bit better than before, like versus 77%. And where's my board? But still not like not high up there. So any questions about the quiz? So I want to give more quizzes. Basically, the point is like if you did not do well in one quiz, you still have chances to improve. But again, it has to be improvement, not like consistently getting things wrong. So we have about 16% of people getting it wrong. Any questions about the quiz? Can you guys hear me? Okay. Are there any questions about the quiz? You should have gotten the results. You should know if you got it wrong. Are they still silly mistakes? Are people still confusing left and right, or still not learning? So this is what I'm concerned about. So I see no questions. I hear no questions. So I guess people are not learning or making silly mistakes. Okay. Can you guys see what I'm seeing? The screen, I'm sharing the screen. You should be able to see that I'm about to draw something. Yes, no, confirm, yes. Okay, excellent. Thank you. If you have any problems, text. I'm getting some blackout sometimes. The screen goes black for an instant and comes back. And in other classes, students said they did not notice anything like that on their side. Okay, so let's clarify the question that we had yesterday. So in order to understand this, we're going to draw field lines going all the way across. So I have to draw them 4 different times. So within this field, we have a wireframe. Let's say it's facing away from us like that. Okay, let's zoom out a little bit. I'm going to make it a little smaller. Like that, okay? So it's facing away from us, and basically, like if you're looking at my screen, you're seeing this, right? While the field lines are going like that. So no field lines are going through the wireframe. The flux is 0. And we're going to label this as A, B, C, D. Now we start turning this thing so that it will look like this. Yeah. Like that. Okay, so A and B, the side AB is moving away from us. CD is moving towards us. Question to all of you. What's happening to amount of flux going through the wireframe as we rotate the frame like that? Okay, so we have 29 people. I expect 29 responses, honestly. It's just so easy to respond in this case. Increasing the flux. The flux is increasing. So as a result, the reaction of the wireframe will be to oppose the change. Not oppose the field, but to oppose the change. Since the flux is increasing, the reaction will be to decrease the flux. And that means the secondary flux will be going in this direction. Okay, is that picture clear? So we're trying to reduce the number of vectors going to the right by introducing vectors to the left. Okay, so now the thumb is pointed to the left, and the 4 fingers follow the wireframe from D to C, from C to A, from A to B, from B to D. So if you can do that, you should actually do that again, hand muscle memory, right? If you do that, you will see that the current has to go from C to D, from A to C, from C to A, I'm sorry, from A to B, and then coming back to D. So that's how the current goes. And we're going to put it here. So the current is going to go up on our side here and down on the other side there. So I'm going to make the eye a little small here. Does this make sense? Okay, it makes sense to some people. So a little bit later, the wireframe will be turned like that. So if I were to draw the normal, normally will be facing this way, pointing this way. It's normal. So in this case, we get the maximum flux, and for the short period of time, the flux won't be changing much. So in essence, you get zero current here. In fact, the change of the flux will be switching its sign. We have been increasing the flux from position 1 to 2 to 3. And now we're going to start decreasing the flux. We're going to go to the position 4. Position 4 will look like this. So now C and D are slowly moving away from us. A and B are slowly moving towards us. They're still over there, but in a little while they will come back. They will come back up towards us, and the CD will move away, recede from away from us. Again, the question is, what's happening with the flux in this case? Okay, your responses will be highly appreciated when I get to grade your work, since we don't have tests anymore, quizzes only. The flux will be decreasing, right? The blue lines coming through the frame, the number of blue lines will diminish, right? So the reaction of the wireframe, and again, this is reaction, like this is what we say, but it's not the order, it's not the way the things go. It's not the order that things go. So I'm going to explain that just a little bit later. Essentially, what we're doing now is we're trying to learn the technique of figuring out the current or the field. So this is our secondary magnetic field. So it's trying to compensate for the loss of the primary magnetic flux. Thus, the change is decrease of the primary flux. How do I oppose the change? By increasing the secondary flux. So the B vector, the pink B vector goes in the same direction as the blue vector. Okay, so now we're going to point the thumb to the right, and 4 fingers follow the wireframe. This time the current goes in the opposite direction. So you should be able to see that. So we're going to go, thumb is pointing to the right. We'll go from B to A, then to C, then to D, then back to B. So that's going to go down on this side. This is very important because, as you see, the current has changed its direction and up over there. Okay, so questions for about stages 1, 3, 1, 2, 3, 4. Questions. Don't be shy. So the fingers, which fingers you mean? So the thumb is where the field is going. Go over, find direction of the current. Okay, so first you have to identify the reaction of the wireframe, right? The reaction in the second stage is that to decrease the flux, because the primary flux is increasing. To decrease the flux, you need to point your secondary field, the thumb, to the left. And your 4 fingers follow the current. So you follow from D to C to A to B like that. So on our side, the current goes from D towards C. Okay, so that's like about that. After position 3, where the flux maxed out, we continue turning the frame. That the flux starts decreasing the primary flux. So in order to compensate, we need to add more flux lines or field lines in this case towards the right. So then you realize that the B, the pink B, should be pointing to the right. That's your thumb. And with 4 fingers, you follow the wireframe, and that creates current, direction of the current. Okay, like that. So you go from D to B, then to A, then to C, then to D. That creates current going down on the side CD. What is orientation of the current and neutral position? Shaz, what do you mean by neutral position? Number 3. So number 3, the wireframe, like we're looking at the wireframe edge on, right, like that. Field lines are going, in my case, from my left to my right. And all these field lines are going through the wireframe. Since there's very little change in flux, when you turn a little bit like that, in this case, the current will become 0. So for instant, for a very brief moment of time. Okay? Frederick, thumb represents the field in all these cases. The pink one. Because that's we want to find out the secondary magnetic field. From Kevin, respond to your question. From 1 to 2, the angle is going from 90 between the normal and the B, which is going like that, the normal, towards 0. So that absolute value of the cosine of the angle is increasing from 0 to 1. Okay? So, and towards position 3, you have maximum flux, because normal is pointing in the same direction as the blue arrows. So theta is the angle between the normal towards the wireframe and the B. Right, you can choose normal to be going into the page or out of the page. It doesn't really make any difference. It just makes a difference in terms of which way the current will flow, like plus or minus. But once it shows that orientation, you stick to it, you will get the same picture if somebody else chooses a different direction. How would you describe the theta in 4? In 4, basically you're moving from 0-degree angle towards 90-degree angle, or if you like, towards negative 90-degree angle. Since cosine is an even function, it doesn't matter if it's negative 90 or positive 90, negative 45, positive 45. You would still get the same value for the cosine of the angle. What matters is that you figure out which way the current flows. Okay, so the way I described this was it's a technique, meaning that we're gonna go backwards. We're gonna kind of reverse engineer. First, we figure out the reaction of the secondary of the frame and figure out the secondary field lines. Then we go back and figure out the current. You have to understand that in reality, like in nature, this happens in the opposite. I mean, the proper order would be that first you have the change of the primary flux. Next, you have this change in the primary flux creates EMF, which is like voltage. Voltage then in turn creates the current, which is the green arrow over there. Then that current in turn creates magnetic field, which will be in such a direction it will oppose the change of the primary flux. Okay, that's the essence of Faraday Lenz law. And then if you follow in that order, this is how things happen in order. And there's always a little bit of lag, a little bit of delay between each steps. Nothing can happen instantaneously. Everything, it takes time. And when we get to electromagnetic waves, hopefully after the break, then you will understand why this lag or delay is important. Okay. The technique, again, that I explained is going backwards. First, you figure out the field, the thumb, and then you figure out the current. But you can always go forward. If you know the current, you can figure out the field, vice versa. Does this all make sense? I really appreciate your questions, by the way. Okay, if it makes sense, then the next step should also make sense. We're going to slide it up a little bit. And what I'm going to do, I'm going to draw the current. So if the current was happening in this wireframe, we would see an interesting pattern. So that's not a straight line, more or less. So this is time, and this will be current. So current goes basically from 0 to maximum, then down to the negative, up, positive, negative, positive, and so forth. Plus, minus. This is direction of the current, not like poles. Okay, like that. So how would you call this kind of electric current? AC, yes, alternating current. This is an example of AC. If anybody would like listen to AC/DC, this is like half of the team. Okay. Now, this was electric motor. This is an electric generator, basically invented by Faraday. And the funny thing is that they were fighting to get DC because people got used to DC for a little while. They use voltaic cells. They use voltaic cells to conduct electricity through salt solutions, all kinds of electricity experiments. And AC was a nuisance, essentially, right? So they had to make a mechanical attachment here that would turn AC into DC. And if you get DC, it wouldn't be perfect DC, but it would at least be pointing in the same direction. So DC would look like this. So it'll be like a bumpy. Basically, reflect all the minus sides to the plus. Okay, this is DC. Not the best DC that you would get, you would want. You wouldn't, like, from the battery, you get flat current, constant current, right? This is going to be like fluctuating. But nevertheless, is a DC, so you can expect certain things that you used to from using voltaic cells or batteries. And surprisingly, this thing was overlooked until Tesla, right? Nikola Tesla came along and he figured out that this is the better way to conduct electricity over long distances. And we'll discuss a little bit of that later when we talk about transformers. One of the greatest fights between inventors of the 20th century, Nikola Tesla and Thomas Edison. So good versus evil. Okay. Okay. So let's explain. Let's see how much time we have. Do I have time? Where's my time thingy? Yeah, this one. Okay, we have time. Let me explain the mechanical attachment that was used to convert AC to DC. How would this be better than AC? Well, again, Shaz. So if you're conducting an experiment when you want to produce pure metal, so you need electrolysis, right? Electrolysis will move the current in one direction only. So on one electrode you get silver, on the other electrode you get some crap. So you want silver, And you don't want the silver to come on and off that electrode all the time, which would happen if you have AC. If you have DC, you would be collecting silver on one electrode, pure silver, or other metal, doesn't matter. So that's why it's better than AC for getting certain things done, right? But if you want to conduct it over long distance, that's a different story. Okay, so I'm going to move this to the left, and we're going to draw an attachment. Basically, things that they came up with. It's a mechanical thing. So let me just move a little bit more. So the device looked like this. So basically, you have I need the black color. So basically, you will have a wireframe, and it will have a longer leg here, a little shorter leg here, and then there will be a cylinder looking like this. It's split into two parts. So not the best way to draw it, but like that's. So imagine a cylinder which is cut into two equal halves, right? They're separated by a certain gap, and the wireframe originally is at 45 degrees in respect to that plane that dissects the cylinder. So imagine also we have the magnet here, north, south, and let's say we turn this. I don't know. Let's turn it this way, like that, right? So turning it this way. So as we turn it, the flux will be increasing. Let's say it's increasing, right? In that case, then the reaction will be to decrease the flux, right? So it's going north to south. So when I change that, so as you turn the frame, we're going to go like that. So the current will be going down. Here, will be going up there. So right now, I'm not really strictly following the geometry, but basically the point is this: is if we have this is AC, AB, I'm sorry, AB, and this is CD. Right now in this orientation, AB has current going down, and that means current is going this way. That's going to be minus. So current is going to go. Well, it's a generator, so it's going to be plus, providing the current. This is collecting the current back, which is going to be basically minus, like that. So in half a rotation, AB will take the position of CD, right? And then in that case, the current will be going up the AB, because AB will be in the place of CD, which means the wire you have connected to this part of the cylinder is still going to be collecting the current. So you still have minus attached to this half of the cylinder. And this side, the CD will come around this way. So in CD, the current will be going down. So which means you will still be having plus sign on this end. So this way you maintain plus and minus. You can always say, okay, this is always going to be plus, this is always going to be minus. On this way you convert AC power generator to DC power generator. One of the problems with that is that mechanical contact here will worn out quite quickly. So they use brushes, and they're called brush, like motors, they're brushes. And they have a flaw that eventually the brushes will worn out. So, or in some cases, that would cause fire or something, because the metal has to move quickly, collect electricity at the same time, oxidizes, that you get sparks, and not really good setup. Nevertheless, that was the only way to do it, and then today we're moving to brushless motors because we have much stronger magnets available. Brushless motors, those who are in robotics probably are familiar with that. Much more compact, much more powerful, and they don't have any like things that have to have mechanical contact. They have friction. Okay, are there any questions about this? No questions. All right, we're gonna move to the right. Okay, so the next question I want to go over is that nothing is perfect, right? There are certain things that cannot be explained unless you look a little bit deeper into the nature of things. So this was an invention of Faraday again. It's homopolar generator or unipolar generator. So basically you have a disc, a metal disc, and why are you doing that? Metal disc, and it will have the axis, right? And it's gonna go that way. And basically you will sandwich it between two magnets. So let's say north here and the south here. Oops. South. Okay. Now the whole thing can be actually the magnet. I'm just drawing like so you can see what's going on. So you can basically cover the whole face with the south part of the magnet and then the whole other face, opposite face with the north. And now over here we're going to draw positive charges. So metal disc will be spinning. As a result, positive charges will be moving along with the disc. So I'm drawing 4 different positions. Okay. So the disc is spinning like so. So this velocity will be going this way, this will be going this way, this will be going that way, and that will be going that way. So question, which way would the force be on the particle here on top? In which direction would the force be, magnetic force be on that particle? Okay, one more time, people wake up. Which way is the force on the charged particle, positive charge on the top of the disk? Use your right hand rule, figure it out. Participation, participation, participation. Okay, you have to make sure you use your right hand, not just like type something if you don't understand. I want to see quiz results to be like almost 100% every time. If you're learning, that should be the case. Okay, right. So it's going to be up. So the force on this one will be up. If you consider the one on the left side here, the force will be going to again outwards, right? And this is also outwards. This is also outwards. So positive charges will be pushed outwards. So if we drew the disk from the side, then basically you have positive charge accumulating on the edges like that, right? And negative charge accumulating on the axis. And if you have some sort of a wire or some sort of a metal connection, right, then this will be your positive end, and off the axis you can collect the negative end, right? So you got the power source now, and it's constant current. This time there's not going to be like bumpy current, it's going to be constant current. Okay, so the way they did this a long time ago is that they would dip the part of the disk, the bottom part of the disk, into mercury. Mercury being liquid metal would be a good conductor, but at the same time it would not create a lot of friction. So they did not use brushes. Modern development is like you use brushes. And again, we don't use mercury that much because we know of its toxicity, especially vapors, right? Back then, they didn't really know and didn't care. And then the main problem you experience here again, that to collect the current, you have to have 2 rubbing surfaces, metal surfaces, right? And obviously there will be substantial friction, which will diminish the output, right? And also you will get oxidation of the metal due to the friction, higher temperature, presence of oxygen in the atmosphere. So over time, this will get worn out. Nevertheless, people build this kind of generators. One is decommissioned in Australia, and it's like set up as an exhibit in the field in one of those universities. I'll post something on the Google Classroom so you can see it. Okay, so it's a wonderful device. You can get lots of current with very small voltage, like 2-3 volts maybe, right? Hundreds and thousands of amps of current. And the problem is like moving the disks. Now, over here. What if we, instead of moving the disk because we have trouble collecting the current properly, what if we rotated the magnets themselves? So we'll have the north, and we'll rotate that, say like that. The disk will be stationary, right? And then here we have the south, which will rotate basically the same way. So this way we are rotating the magnetic field relative to the disk rather than disk relative to the magnet. Will we get the same output, meaning that would we get electricity coming off the disk? Question to the class. What if we change the poles? Shaz, right? Yes. If you switch the poles, you would get the opposite. You would get minus and plus switched around. Or if you rotate the disk the other way. So it changes the polarity. So the question now, if we, instead of rotating the disk, rotate the magnets, would that be the same outcome? Since it's a relative motion. I think you can recall experience from dropping a magnet inside the pipe. Again, question to the class, will we get the same outcome, yes or no? Yes, maybe, opposite. Yes, yes. Okay, so I don't know, maybe yes, maybe not. The question is this: in order to create electricity, right? We know that we have to change the flux. And in the first question, in the first setup here on the left, is the flux changing? We can remember I said you can cover the entire disk, the face of the disk, with the magnet. So we don't need to like have magnet like only covering part of the disk. So if you have the entire face of the disks into two faces, right, covered with the magnets, then the area is not changing, the B is not changing, the angle is not changing, nothing is changing, but we're getting electricity here. Over here, we have the same thing. B is not changing, area is not changing, angle is not changing, but we're not getting electricity here. So here you will get current zero, nothing. So how come in this case we're not getting anything? In that case we're getting something. And it seems like Faraday Lenz law doesn't apply here at all. Any ideas? Carl, yes, I think that makes sense. So in the first case, we had positive charges moving relative to the magnetic field lines. Magnetic field lines are not real, but the charges are real. They're moving and they're crossing the magnetic field lines. In the second case, charges are not moving. Even though the magnet is spinning, you can't say the field lines are moving because they don't really exist. The field is still there. It's not really changing at all. So in the second case, you don't have charges moving relative to the field lines or relative to the magnetic field, and thus you have no current. In the first case, you have current because you have Lorentz force. If you have three vectors, right? V and then B, then you will definitely get the force. So this device is not based on Faraday Lenz law. It's based on Lorentz force. It has nothing to do with Faraday Lenz law. Any questions about this? ¿Tiene preguntas? I think internet broke down. There's no connection. Okay, I'm gonna stop recording. There you go.